Hello, curious minds. Did you ever wonder how a swing moves back and forth so smoothly without ever stopping suddenly? Today, we are diving into the secret behind that steady rhythm, velocity in simple harmonic motion, or SHM. Why don't pendulums ever just zoom off in one direction? Well, that's because their velocity changes perfectly with time, and we can actually find it using some neat math. Picture the displacement of a particle undergoing SHM. It's given by the equation x of t equals capital A multiplied by sine of omega t plus phi, where A is the amplitude, omega is the angular frequency, and phi is the phase constant. Now, velocity is simply how fast that displacement changes with time. So, we differentiate displacement with respect to time and get v of t equals a times omega times cosine of omega t plus phi. This means velocity also wiggles sinusoidally but stays a little ahead of displacement in timing. The maximum speed, or velocity amplitude, is just capital A times omega, which is the greatest speed the particle ever reaches during its motion. Interesting, isn't it, that at the points where the particle is farthest from the center, those extreme positions at plus or minus a, the velocity must be zero because the particle changes direction there. But at the mean position, where displacement is zero, the velocity hits its peak. This dance between displacement and velocity is what keeps the motion going back and forth smoothly. Next time you're on a swing, remember, the fastest you move is right through the middle and you almost stop at the highest points. That's velocity in SHM, neatly captured by our formulas and beautifully visible in everyday swings and pendulums. Welcome back. Let's talk about acceleration in simple harmonic motion, or why that swing feels a pull trying to pull it back to center. Acceleration tells us how quickly velocity changes, and in SHM, it's closely tied to displacement, making it a star player in the show. Since velocity is the first derivative of displacement with respect to time, acceleration is the derivative of velocity, or simply the second derivative of displacement. Starting from our velocity equation, v of t equals a times omega times cosine of omega t plus phi. If we differentiate that, we get acceleration of t equals negative a times omega squared times sine of omega t plus phi. Notice the negative sign? That means acceleration is always directed opposite to displacement, pulling the particle back towards the center. This is called a restoring force in action. Another way to express acceleration is simply a of t equals negative omega squared times x of t, showing the direct relationship between acceleration and displacement. Imagine a spring stretched out. When you pull it to one side, the spring pulls back harder the further you stretch it. Acceleration is greatest when displacement is maximum, that is, at the extremes, and it's zero exactly at the equilibrium or mean position, because there's no restoring force there. In short, acceleration is the invisible tug that keeps the particle swinging back and forth, always opposing the position and at its strongest when the particle is furthest away. Quite the energetic game of push and pull. Hey there! Ever seen those cool graphs where displacement, velocity, and acceleration all wave up and down but don't quite match? That's because in simple harmonic motion, these quantities oscillate together but with different timing or phase. Think of displacement as the main beat and velocity and acceleration as DJs remixing the tune with their own spins. Displacement, x of t, velocity, v of t, and acceleration, a of t, all vary sinusoidally with time, but velocity leads displacement by a quarter of a cycle, or pi over 2 radians, and acceleration leads displacement by half a cycle, or pi radians. Put simply, when displacement hits zero and passes through the middle, velocity is at its maximum. Meanwhile, Acceleration peaks at the points where displacement is maximum or minimum but points opposite to displacement direction, which is why the acceleration graph is flipped compared to displacement. Visually, if you picture the sine wave for displacement, the velocity wave looks like a shifted cosine wave, peaking when displacement crosses zero. Acceleration graph shifts even further and peaks in opposite direction to displacement. And all three oscillate at the same angular frequency omega, keeping perfect harmony. This phase difference is crucial because it explains why particles don't just get stuck or shoot off, they smoothly trade energy between kinetic and potential forms to keep oscillating. Imagine a roller coaster that trades its speed for height all the time. That's a great way to think about energy in SHM. Here, the kinetic energy depends on how fast the particle moves and the potential energy depends on how far it's displaced. Kinetic energy in simple harmonic motion is given by 1/2 times mass times velocity squared. Because velocity varies as cosine of omega t plus phi, k oscillates like cosine squared of omega t plus phi. Potential energy, on the other hand, is 1/2 times the spring constant k times the displacement squared, or 1/2 k times capital A squared times sine squared of omega t plus phi, since displacement is sine of omega t plus phi. Notice that kinetic and potential energies are complementary, they trade off like two sides of a coin. When kinetic energy is at its peak, potential energy is at its minimum, and vice versa. Both energies oscillate at twice the frequency of the simple harmonic motion itself, meaning they complete two full cycles while the particle does one. Despite all this swapping, the total mechanical energy, which is the sum of kinetic and potential energies, stays constant. It equals 1/2 times mass times omega squared times capital A squared. So no matter how the particle swings, the total energy is conserved, just shifting between kinetic and potential, a perfect example of energy conservation in action, like a well-practiced dance. Let's connect the dots between energy and motion in simple harmonic motion, focusing on how velocity depends on position rather than time. Starting with energy conservation, the kinetic energy, 1/2 times mass times velocity squared, equals the total energy minus potential energy. Written mathematically, kinetic energy equals 1/2 mass omega squared times capital A squared minus x squared, where x is displacement. Rearranging this, velocity as a function of position becomes plus or minus omega times the square root of capital A squared minus x squared. This tells us the particle moves fastest near the center, where x is 0, and slows down to 0 velocity at the extremes, where x equals plus or minus capital A. Meanwhile, acceleration at any position x is simply negative omega squared times x, always pointing back toward the equilibrium. This quadratic relationship between velocity and displacement means we can understand the characteristics of the motion without even knowing the exact time. Imagine you're watching a child on a swing and noticing how their speed changes with their position along the arc. The energy perspective gives you a perfect way to predict that speed right from where they are, skipping time altogether. Alright, time for some number crunching. Suppose a particle oscillates with an amplitude of 0.05 meters and an angular frequency of 10 radians per second. We want to find its velocity and acceleration at time t equals pi over 4 seconds. First, recall the formulas. Displacement x of t equals a times sine of omega t. Velocity v of t equals a times omega times cosine of omega t. And acceleration a of t equals negative a times omega squared times sine of omega t. Plugging in the numbers for velocity, we get 0.05 times 10 times cosine of 10 times pi over 4, which simplifies to 0.5 times cosine of 5 pi over 2. Cosine of 5 pi over 2 is 0, So instantaneous velocity comes out to 0 meters per second. For acceleration, substituting values gives negative 0.05 times 100 times sine of 5 pi over 2, which is negative 5 meters per second squared. So acceleration is minus 5 meters per second squared, pointing toward the equilibrium. This makes sense because at t equals pi over 4 seconds, the particle is at an extreme position, velocity is 0 while acceleration is at its maximum in the opposite direction. Numbers confirming theory, physics magic. Let's wrap it up. Velocity in simple harmonic motion is given by displacement amplitude multiplied by angular frequency times cosine of omega t plus phi, while acceleration equals negative displacement amplitude times omega squared times sine of omega t plus phi. And we can also write acceleration as negative omega squared times displacement. Velocity as a function of position is plus or minus omega times the square root of amplitude squared minus x squared, showing how speed depends on displacement. Total mechanical energy remains constant throughout motion at 1/2 times mass times omega squared times amplitude squared. Remember, velocity leads displacement by a quarter cycle, peaking at equilibrium and dropping to 0 at extremes. Acceleration always works against displacement, pulling the particle back toward the center and reaching maximum at the extremes. The energy viewpoint neatly confirms these phase relationships and helps us understand magnitudes and directions without always focusing on time. So, from velocity and acceleration to energy, simple harmonic motion balances forces and energy in a perfect, rhythmic dance. That's it for today's exploration. Physics is fun when you can laugh and learn. See you in the next session.